Hello, this is Freethought Forum, a program of the Atheist Society of Knoxville and the Rationalists of East Tennessee. I'm Faithless Forrest.
And I'm Osama Al-Bini. We want you to know that if you don't believe in God, you are not alone. Right here in East Tennessee, you can find free-thinking atheists and agnostics. This is a show for them and for people committed to a life rooted in science and unfettered by supernatural beliefs.
We will delve into an interesting question about the nature of the universe today. We're going to talk about life in a black hole. We shall review the merits of the assertion that the universe is a black hole.
Well, but first we want to tell our viewers about the show's sponsors.
The Atheist Society of Knoxville frequently has a fun meetup at a bar or eatery. Tonight's meetup is at Barley's in the Old City starting at around 5:30. Look for the silver-jacketed copy of The God Delusion standing upright on the table. And as Matt Dillahunty at Atheist Experience says, everyone is welcome to our happy hour for food, drink, and conversation. But if you plan to preach, proselytize, provoke, or punch, please don't.
The Rationalists of East Tennessee have several regular monthly meetings. The first and third Sunday mornings of the month are usually lectures with lively round-table discussions. The second Sunday, we hold the Skeptics Book Club. On the fourth Sunday, we are mixing it up. Sometimes, with a get-together we call a reflections meeting, it features a potluck lunch in someone's home. Sometimes we meet to play board games, watch a movie, or similar activities. Just last week, we had a picnic for the National Day of Reason.
Oh, that's not a line. It was earlier in the month.
Yeah, that was...
And later in the show, we will give you our websites to visit for additional details, including times and locations. All right, well, we didn't dig up anything for In the News today.
But probably we have something for the news next time when...
Stop in next week when probably the whole show will be devoted to the activity that happened just this past weekend. What happened this past weekend?
The Reason Rally.
Reason Rally. Where was that?
Washington, D.C.
All righty. Well, so tune in next week for what we hope will be the reminiscence of many of our members on that.
Mm-hmm.
Well, so today we're going to talk about life in a black hole, or maybe is the universe a black hole?
Mm-hmm. A very interesting question into itself, but we will try to discuss some topics. But let's start with some issues related.
We'll argue the merits of it. I think that's the point. I like to lead into this by saying that I'm the luckiest person to have ever lived. When I was 10 years old and humans were landing on the moon, many of us shared that experience by television. And this inspired me to an interest in science and the universe around us. And in grade school, junior high school, and in high school, I read lots of popular books on science, many by Isaac Asimov. This is The Collapsing Universe. And even by Albert Einstein. This is your book. I think I've only read half of this. I've read his book on special relativity. This is general relativity. I may have to check this out from the Al-Bini Library.
Well, he's a very wonderful writer, so you probably have a very wonderful time reading it.
And it's amazing how accessible his writing was.
Right.
I think I had read it, and then after the fact realized that, wait a minute, he's not a native English speaker. Even though he grew up speaking German, the result was a book that was still very accessible.
Right.
And for me, special relativity was so exciting because it seemed so exotic and non-intuitive. Now, after high school, I attended the University of Minnesota, and in 1981, I graduated with a bachelor's degree in physics. So what was your experience?
Well, I actually had a very interesting childhood in that I had a mentor. My first mentor was my uncle, and he was a rather bookish person, and very often his gifts would be books. So I ended up reading quite a lot, and many of the things that I ended up reading were science-oriented. So I really owe a lot of gratitude to my uncle for exposing me to all this stuff.
Tell us your uncle's name.
Khalid.
Khalid?
Khalid.
I'm guessing I'm not even close.
It means immortal.
Immortal, all right.
So,
well, the kind of immortality that the only kind there is in the real world is to pass on to people who come after us these interesting ideas.
that's definitely true. And I think one of my first exposures to Einstein was through a TV show when I was in the 7th grade, where there was this host who was supposedly an ex-atheist.
An ex-atheist.
Yes, he became a Muslim, and he was very interested in science. His name is Mustafa Mahmoud. Many people still know about him. And I think there was an episode about special relativity. And I think that was the first time I had this combination of religion and science presented to me, but I had an interest in science regardless of all that. So I started reading a lot of things, and by the time I was starting to question religion, I was also very interested in science. So that was around the time when I was entering college. So I went to college in the Hashemite Kingdom of Jordan, to the University of Jordan. I got a bachelor's degree in physics from that place, and then a master's degree. And all that time I was very interested in the fundamental questions about the universe, about where we came from. And so I ended up studying things related to our topic today in graduate school, which is black holes. And that was the general topic of my PhD when I got to UT and worked on stuff that are related to black holes and the LHC.
So when I was a young man, the exotic stuff in physics was still, well, about which there was popular writing, would have been special relativity and quantum mechanics. There's this thing about quantum mechanics that goes by this sort of a not very explanatory name. They call it the ultraviolet catastrophe. And who doesn't want to read about something that says catastrophe in the title?
Right.
But boy, that's a hard thing to talk about, and we aren't going to talk about that today.
Well, there's plenty.
And it's not very compelling.
There's plenty that we're going to just pretend is not there, and we're going to try to present something that would be accessible to people, and we're not going to be discussing lots of physics that some people think is boring, even though I like to call it fun, P-H-U-N. It's a special kind of fun that only people who are willing to actually invest the time in order to understand would find.
Yes. Yeah, there's a bit of effort to understand. So again, I'm the luckiest person to have ever lived in many ways. And one of the which is that I took an amazing test in my senior year in college. It was the graduate written exam. And it was a test that was going to be given to PhD candidates, and they were expected to pass it within 2 tries. Mm-hmm. But as an undergraduate, we had like a free shot at it. If we passed it, it counted. If we didn't pass it, it didn't count against us. I didn't pass. However, this test changed me. It inspired me.
Wow, that's such a testament for a test. Can you tell us a little bit about what happened there?
Well, I'll tell you and the viewers the story, and I hope to convey this transformative experience. The test led us through the derivation of the formula for escape velocity, the formula for which an example would be, would be to use to figure out the requirements for our rockets to get humans from the Earth to the Moon. So that's kind of exciting. And, well, remember, this would have been only, it was 10 years, less than 10 years after humans were still going to the moon.
Mm-hmm. Actually, I think it would be a nice idea to show the equation on the screen right now.
Okay. And Sam, can we get our Wikipedia equation? Mm-hmm. There we go.
Okay, that's...
So if you have enough velocity, yeah, you're there in the equation.
I'm the radius, I'm the r.
If you have enough velocity, you can fly away, up from the Earth, and then you can get to the moon. Technically, the escape velocity will get you to infinitely far away, and if you're willing to wait long enough. The moon is less than infinitely far away, and if you don't want to wait long enough, you want to give yourself a little more than escape velocity to get there quicker. Otherwise, you'll get hungry in your spaceship, or you'll run out of air. So we've got some things here about the escape velocity from Wikipedia.
Right. So
Do you want to share some with us?
yeah, let me say a few words about it. So escape velocity is actually the minimum velocity that would be needed in order to completely break free from the gravitational attraction of some massive object like the Earth, like the Sun. And for the case of the Earth, it's about 40,000 kilometers per hour, or about 7 miles per second if we convert it to miles per second, which is a really magnificent speed. If we think about the speed that is needed in order for the rockets to actually break free, and we imagine the amount of power that has to be put into that, compare that to what you have in your car, that is tremendous. And so in order to estimate that, I mean, we can do a kind of a hand-waving argument that would lead us to an estimate of the escape velocity. What we can do is to look at the amount of motion that we have, which is contained in the kinetic energy, and then the amount of pull that is contained within the gravitational potential. And if we combine them together, we have the total energy of the system. When we're talking about the object breaking away and going all the way to infinity, we're talking about no kinetic energy and no potential energy. And if we combine the two, we end up with an equation that can be solved for the escape velocity in terms of other things. And these other things are going to be the gravitational constant that appears in Newton's law of gravitation, the mass of the Earth, and the radius of the Earth, or our distance from the center of the Earth.
And that's because we treat the Earth actually as if it was a mass concentrated at a point,
Exactly.
and we're a distance away from it, the radius of the Earth being about 4,000 miles.
Mm-hmm. And so when we end up doing that, you can see the equation behind my head, that gives you the escape velocity in terms of these quantities. So you can roughly look at the equation and see how it makes sense. So if we look at the equation, we see that it has g, that's a constant, and that was measured by first measured by Cavendish.
Henry Cavendish,
about in the 18th century.
I was going to say late 1700s.
Yeah.
Probably was when he was working on that.
Yeah, so he had a very nice contraption that was actually very complicated for the time. He had these two lead balls. They were quite massive. He had them in his shack, and he put things in such a way that he would have this torsion device that would measure very tiny attractions between smaller lead balls and these bigger ones, and the light reflected from a small mirror that is pivoted around the axis would then give him a kind of an angle that he can use in order to see how much deflection happened. And he was able to get a measurement for that constant to within 1% or less, and
of the current value.
Yes,
currently accepted value.
And that stayed for about 100 years without much modification. So he really was able to do a really good measurement. And his measurement is not the only thing that he did. He did so many different things in both chemistry and in physics. So probably not many people know about his achievements that preceded.
It's funny, I know about them once again because of Isaac Asimov and the things that I was inspired to read. Well, so in the test that I took, the formula that we were led to derive, v is the square root, v is the velocity, and then we've got g, the gravitational constant, the mass m, and then we've got the radius of the object or distance. I remember that as I was deriving it, it was kind of remarkable how much coaching they were giving us. It was like they didn't want us to get this answer wrong, and it's like I noticed it as we were working it out, but I didn't realize it until later in the test, and that was because we were going to use this result later in the test. So
of course, if we look at it, it's a mathematical formula, and it can be a little bit of work to get to a point where we can actually understand how this works. Because usually when we do this in an introductory physics test, we have to lead up to it. We first introduce a lot of things, Newton's law, energy, and so on, but we don't have time to do that here.
You also have students who you either understand calculus or you teach them enough calculus to make it happen.
And so we can probably do a small demonstration right now, and we can do it with a ball.
Oh, look, a ball.
Oh.
So
if we look at what the ball can do, we can imagine just throwing the ball up and down, and as you can see, what goes up must come down. This is something that we have all learned,
and kids.
And we always expect that to happen. This is actually part of our evolutionary heritage. We grow up around gravity, and this is something that has shaped so many different aspects of our lives that we don't even expect. But if we want to look at how this relates to the escape velocity, we can start looking at what happens to the ball as we throw it up, or we can also look at other aspects. What would happen if I were to do this?
All right.
The kind of trajectory that took it from my hand to Forrest's hand was a kind of a parabola. If we do it again.
A curve. All right, here we go. Whee! Did we manage to cover the curve on the graph, on the background? All right, again. All righty, so that which is thrown straight up comes straight down. But when we throw it sideways, it follows a curve.
So Newton actually had that exact figure in his book. He would show a cannon that throws projectiles, and these projectiles first, as we experience them in everyday life, would do exactly something like we did right now. They would move in a parabola, and they would eventually hit the ground. But what would happen if you were to shoot that cannon hard enough?
I'm not sure. I guess the parabola is an approximation maybe of something more expansive?
Right. So the actual problem, when we look at the parabola, is just an approximate one. It's not one that represents all the possible trajectories that the ball can take. And you can imagine other types of trajectories.
All right. Well, speaking of imagination, I have found Carl Sagan's, the button to control Carl Sagan's ship of the imagination. And I guess if we're real clever, I can get you to push this button. Are you game to push the button? And we'll use Carl Sagan's ship of the imagination to go further.
Absolutely. It looks familiar, but
it looks familiar. Here we go.
See what happens.
Whoa.
Whoa.
Where are we?
I have no idea. Wow, that's a magnificent view.
All right. Well, so while we're talking about the paths of objects thrown, we've moved ourselves out of the studio and here where we can see the Earth. So we're going to talk about now what the path of objects look like, where we can maybe see the Earth with respect to it.
Mm-hmm.
So what the word we're trying to use is parabola, and a parabola is a curve that's generated because we have a constant horizontal velocity, but the upward velocity slows down, stops, and turns around. That gives us a path that's like an upside-down U. Maybe we can get that next slide.
Okay. Oh, so I see why we're here. Now we are looking at a parabolic trajectory close to the surface of the Earth. Now, we said that this is an approximation, and it's an approximation because it is so close to the surface of the Earth. When you throw something, as you said, you have that constant rate of acceleration downwards, and that's why we end up with a parabola. As we move away from the surface of the Earth, that's not going to be the case.
If we throw a projectile higher, so that the distance it rises becomes comparable to the size of the Earth.
Right, and in fact, what happens is that we get into a different type of situation, which is much more complicated, that has other factors. but we still would have the parabola as an approximation as we get very close to the surface of the Earth.
Well, I guess I'm going to reset the coordinates here on Carl Sagan's imagination machine, and let's see if we can see those other more complicated systems. All right, look at that.
Wow. So
I guess we've got 3 examples here.
yeah, so we have the innermost one, which looks like a parabola. And
Parabola only on the top.
right, so it's an approximation, as we said. So beyond that smaller approximation where you have things close to the surface of the Earth, it's no longer valid, but we continued the entire thing to show the whole trajectory. And then we have
And what is that trajectory?
an ellipse.
An ellipse. So it's really kind of a mistake to say that things travel in a parabola even on the surface of the Earth. It's a good enough approximation for, I think, even artillery and stuff like that, which are pretty long projectiles. But if the Earth wasn't there, if the surface of the Earth didn't intercept your projectile, it would fall and make this.
So the tip of the ellipse looks like a parabola, and even in the case of artillery, they have these tables that take into account other things like air resistance and other complications that we have to add up on top of the.
I'm told Coriolis effect as
Yeah,
well.
so
another thing we're not going to talk about today.
So several complications, and this is an oversimplification of things, but we can see that we have a different also kind of orbit. We have a circular orbit as well.
So the innermost ellipse, that only has a small horizontal velocity, and that's why when the object falls from that height, it intersects the surface of the Earth.
Right.
If we give it more sideways velocity, we get this other shape.
Yeah, so it might be interesting to actually mention in this context what happens in the case of something that's orbiting the Earth. So if you look at people inside the space station, they will look as if they were weightless, when in fact they're not really that far away from the surface of the Earth to actually say that they have broken away from that gravity. They're actually orbiting in some kind of a close orbit, just a few hundred miles away.
In fact, the Earth has a diameter of 4,000 miles, and this circle I've drawn here is much higher above the real Earth than the orbit of something like the International Space Station. It's only like a couple hundred miles up.
Right.
So that's just 1% or 2. So if you were to draw it to scale, it would look like a circle that's almost laying on the surface of the Earth.
Exactly.
And so where they are, the strength of gravity is almost the same
Almost
as it is here on the Earth. It's only the fact that they're in this dynamically changing environment, this circular travel, that gives them the microgravity.
Right. So if we want to describe it with a little bit more detail, we would say that there is a kind of an equilibrium between that situation where they're falling down to the Earth, but at the same time they have a horizontal velocity that is pushing them away so that they're actually falling, and that's what we're experiencing.
All righty. So let's see, we've covered the fact that the Earth's radius is about 4,000 miles. The escape velocity is about 7 miles per second. So what that means, does it mean that we've got to push this object to the side at 7 miles a second and then it won't come back to the Earth? And that'll give us then this long path that never closes back on itself. Right.
So in essence, that the object would never come back, would never fall back to Earth. And that, again, is demonstrated very nicely in that graphic that Newton had in his book.
So, of course, we've only drawn the Earth here, and that number, 7 miles per second, that'll get you away from the Earth. But there's another big object in the vicinity, and that is
the sun.
Our sun. And it turns out, even as far away as we are from the sun, it dominates. You have to add considerably more velocity to get away from the sun. And the numbers, when I looked it up, is 26 miles per second. So as big as 7 miles per second is 26, well, that's a whole lot more.
It's considerably more. Yeah.
And that's why to move around within the solar system requires significantly bigger rockets than to merely go to the moon.
And that's why they don't even rely on the rockets themselves. They very often use the gravity of other planets in a kind of a slingshot effect in order to move around, change speed, and so on. So if we look again at this equation, we see that it's a function of mass and how far away the person is or the observer is from the center of the object. And in your test that you took, they were looking at what happens if we were to replace this with the speed of light, which is 3 times 10 to the 8 meters per second.
Yeah, so this formula has terms like mass, and mass and speed and distance, which is radius. But then the question becomes, what's the biggest speed we know? Speed of light. So they put that into that formula.
Yeah, and we should probably stress the fact that as far as we know, the speed of light is the uppermost limit of speeds for anything material in the universe to move, and so it is the highest speed possible, and this has been tested in many different ways. There are theories that say that the speed of light is not constant, but that's not what we actually observe. So we have the highest possible speed, and then we look at R. What possible value of R would we put? That would be the radius of the observable universe.
And when I was going to college, the observable universe was thought to be somewhere between maybe 10 and 20 billion years in radius or in age. So they probably picked a round number like 15 billion for the calculation. I don't remember that part of the test.
Yeah, actually, for me, growing up, 15 was the number. So until they started modifying it with better experiments, better measurements, we ended up with the 13.8.
Yeah, the 15 was nice and easy to remember because it was divisible by 5. That was the reason I favored it. It was simply a nice round number, and it was about 3 times the age of the Earth. So it was a handy thing to remember. And when more exacting measurements came along, I felt a little bit of resentment that I had to remember such a peculiar number.
Yeah. So we have now 2 elements of this formula that we're talking about. We have the mass, we have R, and let's remind the viewers that G is the constant that Cavendish measured, which represents the strength of the gravitational pull.
And is assumed to be universal, and
yes,
everywhere the same.
So he measured it on Earth, but it was also possible to verify it with other means to say that it's also valid for something about like the gravitational pull between the Earth and the Moon, the gravitational pull between different objects that we can observe, and so it was a fair assumption to assume that it is a universal constant.
All right. So once we take the these large numbers, the speed of light, the size of the universe, the universal constant, plug them all in, we only got one number unknown, and that's m. So if we move to the next slide where we've solved for m, whoops, we missed one. Apparently, well, so what we get is an equation that says that mass is going to be equal to the velocity squared times the radius divided by 2g. And you plug those numbers in, and when I did the calculation, we got 10 to the 55. And 10 to the 55 is kind of an amazing number, but then they also said in the test that it's about 100 times more than the mass of all the known stars at that time. So what do you think of this number, 10 to the 55?
Well, if we were to include everything that we know today, which wasn't known at the time, which has contributions from dark matter, dark energy, everything combined would give us a density that would actually give us get us very close to this estimate. So probably you can, what has been done then is pretty close to reality, even though it doesn't take into account these additional things that were not discovered at the time.
Well, so once again, this is 1981 when I was taking this test. And since then, the Hubble Space Telescope was built. And it was built in part to measure the dynamics of the expansion of the universe. The assumption then was that if we looked at more and more distant objects, we would see evidence that the expansion of the universe was slowing down. I mean, from the 1920s, it had been known that the universe was expanding. But the assumption was that with a good enough telescope, we could measure far enough away that we could then see evidence of slowing down, and that would help us understand what the mass of the universe was, to know if the mass of the universe was just that amount, so that the universe would expand to infinity, but just infinity, or if it was more massive, it might return and fall back in on itself. That was an open question at the time. Well, actually, I should say, at the time, the only mass that we could account for was only 1%, and they could feel pretty confident that the universe had more mass than what was visible in stars.
Right. So what happened, in fact, for the case of observation, is that since that time we have discovered that the visible matter, the matter that is called baryonic matter that we observe in everyday life, that makes up everything that we see, including luminous matter, photons, and so on, only accounts for about 5% or less of the actual material in the universe. But the rest was discovered to be something that we cannot detect directly except through gravitational experiments and through the expansion of the universe, which makes up the rest.
Well, there's one instrument that really helped, I think, put numerical certainty in all this, and so we need to expand our studio once again. Push the button and we'll move.
Ooh, pushing the button.
There we are. So,
well, I know what this is. We're now looking at an explanation of the Wmap, the Wilkinson Microwave Anisotropy Probe, which is a satellite that was launched in around, I think, 2010.
I think 2005. I think results came in.
The results came in at that later. Yeah.
It's a little bit of a blur now.
Yeah. So from the results of the Wmap, there's a lot that has been confirmed. One of them is that they were able to measure the background temperature of the universe, which turned out to be very much close to the expectation, the remnant of the Big Bang, around 3 degrees Kelvin. And another result had to do with the mass of the universe, which was confirmed to be close to the number that you mentioned.
So I like how they figured out things related to the mass of the universe, and that is that from this pattern that's right over your head, that sort of cyan pattern, there is, let's say, speckling in it. And the size of that speckling lets them determine the amount of both the dark matter and the dark energy. And I'll say it's been explained to me that lets it happen, but I've never seen math that demonstrates how the calculation is done. But that, I guess the numbers are something like 70% of the universe is dark energy, 30% is dark matter, and 1% is the matter that we see around us.
About
maybe it's 4% is the matter around us.
4%, yeah, about something like that. And so we end up with this situation where we most of the matter of the universe is not something that we can observe directly, and even within the realm of things that we observe, we expect that there might be other particles that are yet to be discovered, but they're not going to account for anything close to what we're actually attributing to dark matter.
Mm-hmm. So the interesting thing about this measurement, as well as measurements made by the Hubble Space Telescope, is that it was discovered that rather than the expansion of the universe slowing down, the expansion of the universe is speeding up. And it shows in the graph here behind us, it's this sort of funnel that's coming from your direction towards me, but the funnel begins to open a little bit more quickly about halfway in here. Actually, I shouldn't say halfway. It's about a third of the way back, which is about 5 billion years ago. Right around the time our sun formed, the expansion of the universe began to speed up a little bit. And so this then leads me back to the question that stimulated this whole conversation, and that is, what does this imply about the nature of the universe? Is the universe closed, meaning does the universe have enough mass that light can't escape it, so to speak? Is it a black hole? And yet it's speeding up. That seems to argue that, calling it a black hole is not really a good approximation anymore.
Right.
But yet the universe appears to have the mass that would have made it closed.
Yes, that's true.
So there's really, it comes down, what we've learned comes down on both sides of the question. It says yes and no.
Yeah, so if we look at this analogy, there's plenty of things that would tell you, it looks like a black hole. There was a singularity at one point, a singularity being the main...
Which is that thing over your head.
Yes.
That the beginning of this sideways cup object, I guess.
Right, so we can pretty much describe everything in very great detail up to a fraction of a second of that instant, but then our knowledge basically goes away. So many people say the Big Bang is the beginning of the universe. Well, the Big Bang is actually the end of where we can say things confidently about the universe. And so what we do know is that...
When you say the end, it's because you're sort of intellectually sitting here where I am at the funnel, and you're looking back. So if you look at the graph, you're looking back towards it and saying, well, that's the end of what I can see. But it's really the beginning of what we can talk about.
Yes.
All right.
Yes. And so at that point, if we trace back the history of the universe, and essentially that's the result of the observation that Hubble made, everything seems to be going back to a single point, a very tiny region of space-time where everything was condensed. And then that's the starting point. So it seems that there was something that looked like a black hole at one point in the history of the universe. But would we say that our universe is actually a black hole or not? As you said, that doesn't seem to be the case for many different considerations. The first one has to do with the fact that, the universe is expanding and it's accelerating also.
Yes.
So it seems to be doing the reverse of what you would expect from a black hole.
So now that we've gotten to this point where we're talking a lot about black holes, and I've noticed the time, and we should probably do our program break, and then we'll have about a third of the program left when we come back. So let's jump into that. Viewers, in case you're just tuning in, this is Freethought Forum, a program by the Atheist Society of Knoxville and the Rationalists of East Tennessee. Freethought Forum is funded jointly by them and by individual contributions.
Shows are live most every Tuesday from 5 to 6 p.m. Eastern on Knoxville Community Access Television, Channel 12 or Channel 194, depending on your local cable network. Tell your out-of-town friends to see us streaming online at ctvknox.org.
Today's show is live, June 7th, 2016, and you can call in on the number on your screen and speak with us. If you got questions about the cosmology we're talking about, or if you care to tell us the theories you've heard, that'd be great. And we're going to take a short video break here.
If you live in or around the Knoxville area and are questioning your religious beliefs or simply believe in one less God than everyone else, well, you're not alone. The Atheist Society of Knoxville is a fun and friendly group of people just like you that meets twice a week at a bar or restaurant. We meet every Tuesday night following the show at Barley's Tap Room and Pizzeria for happy hour. You'll find our group either inside or on the patio. Look for Richard Dawkins' silver-jacketed book, The God Delusion, standing upright on the table. On Fridays, we meet at Agave Azul or the Beard and Beer Market. But if you plan to preach, proselytize, provoke, or punch, please don't. We all question what we believe at one point in our lives. If this is the time for you, come join us for food, drink, conversation, and fun. Do you find stories of talking snakes laughable? Do you prefer the scientific method over supernatural beliefs? Are you concerned about religious leaders and organizations imposing their values and rules on your body, your family, and the rest of our society? Well, take comfort in the fact that you're not alone. The Rationalists of East Tennessee meets weekly for fellowship and provides a forum for people who support skeptical thinking and rational discussion of these and other issues. To find out more information or to find out about our next meeting, visit us on the web at www.rationalist.org.
All right. The Atheist Society of Knoxville, or ASK, meets twice a week. We have evening meetings for food, fun, drink, and conversation. ASK's purpose is to provide a venue for camaraderie, community, and outreach to atheists, agnostics, freethinkers, and like-minded persons in the East Tennessee area. Our Tuesday meeting is going on now at Barley's Tap Room and Pizzeria in the Old City. And recently, some of us even went up to Washington, D.C. and saw some of the stars of the Freethought movement.
The second Sunday of most months is the Rationalists of East Tennessee Skeptics Book Club. The title of the next book, what is the title?
It's the June book. It's Unfinished Business, Women, Men, Work, and Family.
And that's going to be on Sunday, June 12th at 2 p.m. The public is invited to participate. You need not have read the book to attend, but of course it helps. Visit rationalists.org to find the rest of the calendar of books and join us at the new location, Books A Million, at 8513 Kingston Pike, Knoxville, Tennessee.
All righty. Well, so today we are talking about black holes and the stimulating experience I had while taking a test.
So, what...
Can we get back the Wmap image to the background again? There we go.
Right. So this is, if we look at that cyan region that you were talking about, this is actually a very interesting and very detailed map if we want to look at the different regions. It shows a lot of the features that represent that region in space that we can see the farthest in space. Beyond that, we are unable to see anything because light wouldn't essentially be reaching us.
What we're seeing in the cosmic background radiation is sort of like the equivalent of an electrically conductive surface that had a little texture in it. And we can't see through it. It's almost like further in the past is like it's hidden behind a metal. We can't see through metals because they're electrically conductive. And the universe was ionized, electrically conductive, before the cosmic microwave background radiation decoupled from it. And so therefore it represents the oldest thing we can currently see with technology we've implemented. There's some interesting hopes for further back, but
we have no idea what the future might bring in terms of technology. So right now, with the limits of what we have, this is the furthest that we can see. But Wmap had an improvement on it using the Planck telescope, which actually tweaked some of the measurements for the age of the universe and
and I think they're doing some polarization measurements as well.
Right. So some of the experimental results that you can get from that match up with what we have very, very nicely. There is a very nice famous curve where you can match up the experimental results that you extract from that map, and you lay it on top of the theory, and it matches perfectly. So as far as we know, our theory that is based on the Big Bang combined with what is called inflation, these things seem to describe things pretty well experimentally.
So we haven't mentioned inflation for the viewers. The Big Bang, well, you used the word singularity a few times. I tend to, if I use the word singularity, I almost always qualify it and say, you know, we haven't measured the singularity. That's behind that area where we can't see. What we do know with confidence is that the universe was much denser and much hotter in the past, and we can call that the Big Bang as well. because the term Big Bang was actually invented by a critic of the theory as a derisive term, saying, well, it was this hot explosion thing. Well, it was hot and it was expanding, and that's something about which we have great confidence.
Right.
Now, the microwave background radiation happens when the universe cooled enough that hydrogen nuclei combined with protons combined with electrons became neutral, and the light that was otherwise sort of contained within this could shine free.
And that's basically the only way that we can receive information right now about what's happening. But right now there is an additional piece of information that could help us, which is...
I want to talk about something, and that was how old was the universe when that happened, and how big was the universe when that happened?
You mean the initial formation of...
The recombination is where I'm going. So recombination is when the electrons and protons bound together.
I can't put a number right now.
It's on the order of oh man, I'm going to say 30,000 years, and all of a sudden my brain said, wait a minute, is it 300,000? It's 30,000, I think, because I think by the time we get to around 500,000, about half a million years, there may be some evidence of star formation.
Yeah.
So
I think last week they were talking about 13 billion something galaxies that were observed, proto-galaxies or something that is that ancient. But I wanted to add that even though we use light today in order to get information about that early time, there might be a way to also extract some information using gravitational waves. And gravitational waves, there was a hype not long ago, if you remember, when they thought that there was an observation of gravitational waves that date back all the way to the time of the Big Bang.
In the microwave background, they thought there was an evidence of it.
Right.
But apparently upon further skepticism, they said, wait a minute, there's a different way to explain it, and that other way is probably more correct. And I guess it has to do with it's either dust or charged dust in our own galaxy that polarizes the light.
Yeah, so observationally, they present the same kind of result, and so it was a little bit easy to confuse the two, but upon further study, upon looking at the data in more detail, it was actually clear that they were looking at dust, even though on the face of it, it looked like they discovered something that goes all the way back to the beginning of the universe. And so if we look at that time, why is it that we're having issues understanding what went on at that very moment at the beginning of the universe? It all has to do with the fact that we cannot combine quantum mechanics, the theory that we use in order to understand the very small, with gravitational theory, which is represented by general relativity. So combining these two in what is called quantum gravity, a theory that we don't have right now, is the only way that we know of that would give us a good description of that period of time, and we do not have it. That's why this period of time represents the beginning of what we know, but if we look further into the side away from the beginning.
Coming towards me.
Yeah. But before that, we don't know much, because that's the quantum gravitational regime. And so that connects the Big Bang to black holes. Why is it that there is a connection between the two? Because in both cases, we're talking about very tiny objects where you have very big masses. And the description that we have that for the first time gives a hint of a way to describe that is through something called Hawking radiation.
All righty. But Hawking radiation wouldn't be this Big Bang heating or anything.
No, absolutely not. Hawking radiation, if we want to look at Hawking radiation as something that can be measured astronomically...
Could in principle be measured. It
Well,
hasn't been measured yet.
Yeah, and one of the reasons is that because if we want to look at its correlation with mass, big astronomical black holes would not be good sources for observing it because it would be a very weak signal.
So that's because a large source, a large mass, has a small signal.
Mm-hmm.
That a smaller black hole actually radiates higher.
Higher and in a very...
stronger, I should say.
Yeah, so the rate of radiation would be stronger. And one of the hopes at the LHC, something that has not, the Large Hadron Collider, something that has not been observed so far, is the possibility of producing these tiny black holes in the collisions and then observing the result.
And meaning that if a tiny black hole was produced, it would decay with a spectrum that would be recognizable,
right.
A characteristic spectrum.
Right, and so a classical black hole, one that is completely described by general relativity, would not radiate. It would be that singularity that we talked about. Mm. But when you introduce quantum mechanical effects, it starts having evaporation effects where you would actually eventually get the black hole to radiate.
So by evaporation, meaning that it loses mass.
Mm-hmm.
In other words, it's not black anymore. Stuff escapes it. Now, I can't help but say, at this point, our universe appears to have the possibility of escaping its confinement. And in that sense, that's another thing that says, well, all right, now it's a little bit like it again. Mm-hmm. Now, what's happening with a black hole, though, is that as it loses mass, it gets smaller. And the characteristic that we talk about is its surface area gets smaller.
Yes.
Now, our universe doesn't look to be doing anything like that yet.
Yeah, that's one of the other indications that would tell us that our universe is probably not a black hole.
So maybe there's a more general kind of object we should be thinking of, these bound radiating objects, but they're so utterly different in size, I guess.
Yeah, so another object that might hold some resemblance to the history of our universe is called a white hole.
All right, have we found any of them?
We have not. This is a hypothetical object that is obtained also from general relativity.
All right.
And it's basically the object that we would obtain by reversing the time for a black hole. So whereas a black hole would suck in matter and nothing would escape it, a white hole would actually be emitting or having things go outside it,
and nothing could be forced into it.
Yes.
So it would be the mirror image. So when you say time reversal, I can't help but think that some viewers might think, well, that sounds like nonsense. But I believe invoking time reversal was what led people to speculate about the existence of antimatter.
Right.
That the equations that were developed to describe electrons and protons, someone said, well, wait a minute, we can reverse the signs on this, and it's all perfectly self-consistent.
Exactly.
Maybe that means there is something out there that'll look like an electron, but with a positive charge.
Exactly.
And lo and behold, it turned up in particle accelerators.
So that was one of the predictions of what became known as quantum field theory. It was started very early in the 20th century. It wasn't still known because the formalism for it wasn't developed yet. But once it was understood and people started looking for it, the anti-particle for every particle was found. So you start with an electron, you have an anti-particle for that, the positron. That's not a construct from Star Trek. This is a real thing, and it has been observed, and it is produced in the lab. This is something that can be seen. You have a proton, you have an anti-proton, everything the same except for the charge. And so on. You can do the same for all particles.
What's amazing is even the neutron, which is neutral, has an antiparticle, and it's not because it has the opposite charge. It is opposite in yet some other way.
Right. So you have other ways of distinguishing these particles. I don't think we have the time to go into it. We can introduce other ideas for it. But yeah, any particle that we can describe quantum mechanically would have its antiparticle. And basically, the way that you can create any of these is if you have enough energy that would represent twice the mass of that pair, then there's a probability of creating it.
And that's, and you say pair, that's why you have to have twice the mass, because you can never make one without making the other.
Exactly.
The universe is like, there may be no God, but the equations are like a relentless bookkeeper, and the books always must balance. Whenever you make a plus, you're making a minus.
Well, that's an interesting point, because if you look at everything in particle physics, you have symmetry, but at the same time you have symmetry breaking. Mm-hmm. So let's look at the case of particle-antiparticle. If you look at the equations and how we understand them, we should expect the same quantity of antimatter to be existent in the universe as regular matter, but that's not the case. And so there is plenty of speculation right now, so many different models that are trying to account for that discrepancy. And we have some idea about where to find it, but the lack of experimental verification for that is causing...
well, this is referred to as charge parity violation, and I thought that was experimentally observed, that if you simply count, you observe the lack of parity, and I assumed it was...
Well, the problem has very various aspects, and especially when you're looking at the cosmological observation, or rather the astronomical observation of the abundance of antimatter as opposed to regular matter, you see that there is a clear discrepancy.
All righty. We're getting kind of close here. I think we should push the button one more time, get back to our studio.
Okay.
Do our button push. There we are, back to our familiar studio. Oh. So, I hope that maybe viewers were interested in the discussion about what I've, since 1981, when I took my senior test, first became aware of this whole idea of, is the universe open or closed? What might that mean? How much does the universe weigh? And I especially hope that maybe some of the younger viewers out there will be inspired to pick up maybe some of these books like this by Albert Einstein himself. This is a pretty readable book. Mm-hmm. I think it was in junior high school that I read the special relativity part, certainly by early high school. And almost anything by Isaac Asimov is a really good read. My first exposure to particle physics was a book called The Neutrino. And it was a marvelous thing. I'm sure I read it in junior high school, if not grade school. All right, well, we're going to need to begin the wrap-up here. It is, get out your pen and paper. This has been Freethought Forum, a program by the Atheist Society of Knoxville and the Rationalists of East Tennessee. I'm Faithless Forrest.
And I'm Osama Al-Binni. Please send us feedback. Leave voicemail at 865-272-9060 or email us at freethoughtforum@yahoo.com.
You can see this show on most Tuesdays from 5 to 6 p.m. Eastern Time on this Knoxville station, and at 2200 Greenwich Mean Time worldwide on ctvknox.org.
The opinions expressed on this show are of the host and guest, not any official opinion of the Ask or RET. We would like to thank
Sam
for technical support, the staff at CTV Knox, and to all of our viewers and callers.
All right, nuns, those who identify with no religion, are the fastest growing religious group in America. Remember, if you don't believe, you're not